After graduating from Princeton, she came to her senses and crossed to the better side of the Delaware River to join us here at Penn. And within the GRASP lab, she's known not only for her research, but also for her impressive napping abilities. As a passionate napper myself, who has, in most desperate times, slept in the fourth floor bump space floor, I appreciate her skills and plan someday to challenge her to a nap battle. So look out for that. But for now, enjoy her sassy quadrotor research. I'm sure if I challenge her in a nap battle, she, like her quadrotors, will persevere and defeat me. Enjoy Sarah's talk. Or maybe in a few seconds, enjoy Sarah's talk.
All right, thank you, Naomi. And like Naomi said, I'm Sarah, and today I want to tell you about some work I've done in the last year and a half on planning for aggressive maneuvers for a quadrotor with a cable-suspended payload. So today, there are many tasks being done by skilled helicopter pilots, and this includes things like transporting heavy objects or bringing raw materials to remote build locations. And here you have this pilot that's bringing gravel onto a hiking trail. And these pilots also help in large-scale construction tasks. So research in oscillation suppression during these kind of transport tasks has been going on since the 1960s and is still an active area today. But traditionally, most work has focused on things like payload oscillation suppression for cranes. In the area of aerial vehicles, in 2007 was the first successful demonstration of autonomous payload transportation by 3 cooperative helicopters. And more recently, there's a group at the University of New Mexico that developed a learning algorithm that can guarantee an upper bound on the load displacement. Now, these payload suppression techniques can allow for fast transport, but would preclude tasks such as this one. So this is a video taken on a Christmas tree farm in Oregon, where a helicopter pilot picks up trees from the forest and drops them onto a truck. And this is actually a much more efficient way to do this than driving the truck directly into the field. Another example of a really aggressive helicopter maneuver by pilots is this footage taken in Portugal. So here, to put out this fire, this pilot actually goes into a neighbor's backyard and picks up a bucket of water. And you can see that he has to maneuver into this really tight space to be able to accomplish this task. So you can imagine that this traditional approach of minimizing payload oscillations would not allow us to autonomously achieve tasks like this. And specifically, we're missing 3 things. First is this pilot's ability to stabilize during these large load swings. So what if we had an autonomous vehicle that could plan and control these swings instead of trying to suppress them? Would this allow us to accomplish tasks even faster or even accomplish previously infeasible tasks? Second is this idea of interacting with the load through pickups and releases. So what if we had an autonomous system that, given an object's location, could autonomously pick up the object, and given a target location, calculate the position and velocity needed to release the object so that it'll land in the right place. And finally, we need to have safe navigation through these cluttered environments. So the goal of my work is to develop algorithms that can enable this new class of tasks. And specifically, we want to satisfy these 3 objectives. First, we want to control rapid and dynamic motions. We want to enable not just transport, but manipulation of payloads in the sense of releases and pickups. And finally, we want to be able to guarantee safe navigation through cluttered environments, even in the presence of potentially very large load swings. So the platform we use for this is a Quadrotor. Like the name suggests, a quadrotor is an aerial vehicle with 4 rotors, and you navigate the vehicle by changing the thrust applied by each of the rotors. We use an electromagnet to pick up and release loads. And this entire system of the quadrotor and the payload I'll refer to as our system. So to develop this autonomous system, we need to design 4 things. First is this dynamic model, which means what are the analytical equations that describe how the payload and the quadrotor react to different forces from the rotors. We need to be able to sense the position, velocity, and orientation of all the objects. We need to have a planner that can plan desired trajectories. And when I say trajectory, I mean a time parameterized function that describes desired position of the quadrotor and the payload. And finally, at each point in time, we'll have a controller that takes the desired position from the planner, compares it to the actual position sensed by the sensors, and determines the inputs to the quadrotor in order to drive the actual positions to the desired ones. So for my talk, I'm going to assume that we have sensing through an external motion capture system. And we have a controller that can allow us to exactly follow any trajectory we plan. And I'm going to focus on the dynamic model and the planning aspects. So for our dynamic model, we need to be able to incorporate these load pickups and releases. And in order to do this, we need to model both the case where the quadrotor has the payload and the case where it doesn't, and be able to transition arbitrarily many times between these 2 cases. So first, in this case, or in this subsystem, we have the quadrotor carrying the payload to some target location. In the second subsystem, the quadrotor has released the payload, and the 2 are acting as separate objects. We transition from the first to the second subsystem when an object is released, and vice versa when an object is dropped. And this is really cool, because by modeling things in this hybrid way, we can actually mathematically incorporate the kind of load interactions we want in one dynamic model. And the last portion of this is the planning aspect, which is where most of my work was done. And again, we want to have a planner that can incorporate dynamic motions, plan for load pickups and releases, and enable obstacle avoidance. First, consider the case where the quadrotor is holding a payload. In this situation, what we care about is the position of the load. So we'll plan a trajectory for the load. And when the load has been dropped, we'll plan for a trajectory for the quadrotor. Now, to incorporate these large dynamic motions, we'll leverage a property called differential flatness. So suppose we have this load trajectory here. What differential flatness tells us is that we can actually back out from this load trajectory the desired positions and orientations of the cable in the quadrotor. Intuitively, you can think of this as saying, if I know exactly how my load needs to move, this will determine the angle and tension I need in my cable, which then determines how the quadrotor needs to move. If we have a slow-moving load, then it'll remain directly below the quadrotor and show this kind of swing-free motion. But if we have a fast-moving load, we need to have these large swings in order to achieve the desired speed. The key insight here is that when we design a load trajectory, we've actually already implicitly determined what the swings will be. So we actually don't need to do any extra work to have these large swings in our maneuvers. So the second question is, how can we design when and how we'll do these load pickups and releases? And the challenge here is we have this hybrid dynamical model where we're saying we can design the load trajectory and the quadrotor trajectory separately. And how can we guarantee that these 2 trajectories will actually agree with each other? So consider this situation where you know the start and goal position of your load and your quadrotor. We will accomplish this planning in an iterative manner. So first, we'll plan the load trajectory completely, including this portion at the end where it's in free fall. We then go back and identify portions on the trajectory where the load is being picked up and dropped off. And from the differential flatness property I talked about before, we can back out the quadrotor position at this time. We then go back one more time to plan a trajectory for the quadrotor from its start position to the pickup position, and a second trajectory from the release position to the final goal position. So what does this put together look like? So first, we start with a quadrotor without a payload. It'll fly to the planned load pickup position, pick up the load, follow this desired load trajectory that we've planned, release the load at the desired portion, at which point the quadrotor will follow the desired trajectory to its final location, but the load will actually free fall into its target spot. So this kind of sequential planning guarantees us that we'll always be planning load and quadrotor trajectories that agree with each other. And using this technique, we can fulfill our requirement for load interactions. So the last question is, where do these magical trajectories come from? And more importantly, how can we guarantee that we're not colliding with the environment? It turns out we can actually model this obstacle avoidance requirement in an analytical way. We model all of the obstacles in our environment using bounding boxes. And we find the normal vectors to their faces and use that to tell us which direction outside is. And we say that the quadrant on the load has to be outside one face of each obstacle. This problem can be formulated as a mixed integer quadratic program, which is something that any commercial solver can solve for us. So in conclusion, we have this algorithm that can ensure dynamic motions, load pickups and drop-offs, and obstacle avoidance. And here are some results that we've been able to implement in our lab. So here is a demonstration of the load being picked up and dropped off. And you can see that the cable actually reaches the load at an angle. And this means that the quadrotor never has to move exactly above the object. So the second experiment shows obstacle avoidance. So in this case, the height of the quadrotor and load and cable is greater than the window it needs to go through. And we can generate this large swing in order to bring both objects safely through the gap. And I think this really demonstrates the necessity of what we're doing. Because if the system were constrained to move in a swing-free fashion, it wouldn't be able to clear this obstacle at all. So what's next? So one direction is really to bring this outside of the lab by doing all of this with onboard sensing. And if we can accomplish that, we can do a lot of tasks. So there are already a lot of companies, I'm sure you've heard, that are thinking about doing delivery of packages with autonomous drones. But with this additional capability, we would be able to do other tasks like putting out forest fires or bringing you Christmas trees. And the second area is that the kind of model we use for our system is actually found in the dynamical systems of many other disciplines. So one example is divers, when they're ascending from diving, they actually need to take these decompression stops so that they don't get decompression sickness. So this can be modeled as a hybrid dynamical system where in one subsystem, the diver is ascending, in the second, the diver has stopped, and so on and so forth. And we can use this to plan optimal trajectories for the diver to get to the surface of the water. Another example comes from electrical engineering. So if we have this converter circuit with a switch, in one subsystem, the switch is closed, and in another system, the switch is open. And typically in this type of problem, the problem is how do we control the opening and closing of the switch to get a certain output voltage that we want? And finally, in biology, we can model these neurons firing. So if neighboring neurons fire, the membrane potential in the neuron will start to increase. After it hits a threshold and the neuron fires, this potential goes back down into some resting potential. After some refractory period, then the potential can start increasing again. So the question I want to ask then is, how can this optimization, iterative trajectory planning approach we use for our example system apply to a more general class of hybrid dynamical systems? So in conclusion, I've told you about some of our algorithms for autonomous, rapid, and dynamic transport of suspended payloads. And I hope I've been able to convince you that this is an important research area. On the application side, I think it can bring automation to a lot of new industries. And on the theoretical side, I hope I can use this example to find insight into a broader class of hybrid dynamical systems. So I just want to end by acknowledging my advisor and everyone in the MRSL lab. They're all working on some really, really cool things, so I would encourage you to talk to them about their research if you get the chance. Thank you.
Thanks, Sarah. Questions from the judges?
Maybe I'll start here. First of all, I was very disappointed. You're moving boxes, not Christmas trees. I think you should fix that for future videos. You know, the proof is always in the pudding, and you just showed us a video of this quadrotor achieving this very smooth motion, so that was very nice. I noticed that the response was quite smooth. In your mathematical model, I know you treated it very topically given the broad audience here, but in your mathematical model, are you controlling for jerk? The third derivative of position?
No, so it's only a proportional derivative.
Okay. Okay, but it's still very, very smooth.
Yeah, so the key is actually in the controller that we use. So there's a literature in here called geometric control, and that allows for really accurate tracking of these kind of progressive features.
It just kind of falls out naturally from that. That's beautiful.
Max?
Well, it was a beautiful talk, and I want to thank you. It was just lovely. Now come my questions. Noise, uncertainty, wind gusts. How do you handle all that? Because I didn't hear anything about that kind of uncertainty in this setup here. Are you doing planning and then replanning as you go along, or is this done? Is this planning really done offline and handled as sort of an input to the overall running of the problem?
So for this, I guess this preliminary stage, we're assuming, as you said, a perfect environment, and we're assuming that we have an environment with static obstacles, and we can do planning beforehand, and the environment won't change. And of course, all of these you mentioned will come into play later on. And actually, this would be a good time to mention that Cedric in our lab is actually working on addressing some of these issues. He's looking at applying iterative learning methods to this kind of controller. So if there were a disturbance, you might be able to learn that and compensate.
How do you model the disturbances? That's a big deal.
Yes. So if you're taking a learning approach, I think the argument for using a learning approach is that you don't need to explicitly model your disturbances. And by running trials of your learning algorithm, you just know how your quadrotor is moving wrong and just compensate for that. And I think that might be the benefit of this type of research.
There are people who fly airplanes in and out of major airports, and they worry about something called wind shear, where you get a surprisingly bad downdraft on the airplane, and it pancakes into the earth and kills everyone. No one has managed to learn how to plan for that. The usual rule of thumb is you just stay the heck out of those areas where you're getting wind shear, and you wait until it's safer to land. People try to measure it by doing fancy things with looking at the way air is flowing and on and on and on. It doesn't seem very safe at this point. I have this, I really like your talk, so what I'm about to tell you is totally unfair. You're telling me about someday Amazon's going to deliver me my book. Okay? I just got a lovely book on quantum mechanics today. And I have this this nightmare that it's going to drop into the Schuylkill River as it's passing over Philadelphia and coming to Rittenhouse Square. So tell me I'm wrong. Well, okay.
Give me like 10 years now. Okay.
Michelle?
Just a quick question. So usually with hybrid dynamical systems, there's sometimes that issue of chatter where you're going in between the different states that you're trying to control. And then so I wondered if that's a problem here. And then the second part is right now you're using a magnetic sensor to grab a magnetic basically in your real life scenarios, you have to actually pick up with the water. I think that seems a little bit different in terms of this challenge that you accounting for. So I'm asking that question.
Okay, so the first thing, chattering was definitely an issue in my implementation of the video you saw. And to deal with that, I put in a delay. So I'm using the Vicon system to tell me when the for example, the Quadrotor load has to be the cable length apart for a certain amount of time before I say that this is finished. So that was what allowed me to do that. So initially, you're right. When I wasn't doing that, the Quadrotor would think it picked up the load and overcompensate and just crack through the wall. Sorry, remind me.
I would say what would change, I mean, you have a simplistic load pickup.
Right.
So what would change if you went now to a simplistic type load pickup where you showed that vision of a water pickup? How would your model change if you had to now deal with those types of graphs?
Yeah. So I guess in a real life scenario, the closest, one of the closest thing that comes in autonomous pickup is to say, well, maybe we have some sort of hook mechanism at the bottom of our table, and our objects are arranged very nicely, where all the I guess things that the hooks connect into are straight up, and in that kind of organized environment, this might work. But that would also definitely need new types of sensors to figure out how to approach the objects.
Thanks. So that is all the time we have for questions for Sarah. However, feel free to approach her during the happy hour. And